Please stick the PAS in the chat for us. Can somebody quickly download that PAS document and stick it in the chat? And then you guys can look at that. But your PAS will be right there where I showed you where to go, where mine is just not working because it says access denied. And then what also there is, if you go back home, you will see student material. Okay, you'll click on student material. And then here you will find your assignments. Okay, I'm going to look for SMAA. I see everybody's everything. So on the one end, I don't have access, and on the other hand, I have all the access. So we're going to look for SMAA 8411 2026. Term 1 is you guys. And we're going to look at assignment 1. Remember that there is preloads that you need to download. I'm going to download both of these for you guys right now and also share them in the chat. And then let's just open that assignment and have a look. Okay, and then we'll start with logistic regression. Okay, so here is your assignment. All right. So the assignment instructions is you must read through chapters 2, 3, 4, and 5 in the prescribed textbook. It's not that. You can read through it, but that textbook can throw you guys for a loop. I think rather just go through the course material we did for that would have been done for KNN's logistic regression, and then obviously Gareth's workshop he'll do with you guys on Friday. Okay. So you will need to do additional research from reputable sources for some of the questions. You will need to write up a summary of many of the questions as well as a full report on a data set. Use Microsoft Excel for only data analysis, data modeling, and graphical representations. Referencing requirements is you use the normal IIE referencing. Okay, so you guys can reference Harvard Anglia, but you also, if you are a computer science person from another institution who's joined us, you are also very welcome to reference ACM. So both the ACM is a numerical referencing style. Okay, so question 1 is theory. So people have approached this in 2 ways in the past. Some people have typed the theory into an Excel document, and some people have had a Word document for theory and an Excel document for prac. Okay, so that is up to you guys what you want to do. Okay. So question 1.1 is describe nominal, ordinal, interval, and ratio scales with examples and explain how their scale type impacts statistical models. So that is audit list, unaudit lists, all of that kind of stuff. Okay. And then obviously it has an impact on statistical analysis if stuff is audit or not audit. Oh, I'm always giving you the answer for the assignment here. Okay. Then define and contrast a training error versus a test error. And we're actually going to talk about that nicely today. But remember that you guys need to also go read additional sources and just cite them. So GAMS is the next class you guys will have next week. You will cover GAMS, generalized additive models with Daryl. So he will go through GAMS there. But if you want to start the assignment already, just go read up on GAMS. They're very easy. You should be able to clearly explain the bias variance trade-off by now. I think Nadia has done that with you guys. If you want to, I can make you a short video. I am making you a short video for question 1.5 to show you how to actually, I will go through lasso and ridge and the elastic net and show you how they are applied and how we calculate them. But just understand, guys, you will never be asked to actually calculate the shrinkage models. You just have to know what they are and why they are applied. And if I go through that in that video, which I'll upload tomorrow, you will also clearly understand the bias and variance trade-off. We go through that very slow and in detail in that video. As well, also I've given you the link to all of my recordings for last year where I go through all of this. Okay. Then, so that's question 1 for 35 marks, which is largely theory, which you could do in an Excel doc. You guys, just be careful if you embed word snippets in an Excel doc. It often doesn't pull through. So if you're going to do it in Excel, you're going to nasty type that in an Excel cell or do a separate Word document for theory and an Excel document for prac. Then for question 2 for linear regression, so here they're quite specific, where they say you're going to create a PDF that has a report. Okay, that will show you executive summary, aim of the study, results and interpretation, your conclusions and recommendations, and then an Excel worksheet where you've done your working. So all they want you to do here is apply logistic regression and then look at that R2. Okay, logistic linear regression, and look at your R2 score, which is a percentage out of 100, and say if you can trust this model or not. So let's look at the questions and let's go through how we would do that. So the question says, it's hypothesized that a student's performance in an examination depends on the number of hours spent studying and the number of past examination papers reviewed. You are provided with a dataset multilinear regression, which is what we did in the last class, containing the following features. Hours studying, preparation exams taken, so just 2 features, and marks out of 100. Now, if they're going to ask you to compute Pearson's correlation, and I mean, guys, sure, that's hard, eh? It equals coral. And for hours studying and marks, I mean, that's for free. That's just that little coral function. Okay, and then they're going to say using Excel, fit a multiple linear regression model to predict marks using both predictors. So remember what I told you guys. Oh, this is all off here. Remember what I told you guys, even though I have taught you to now go and actually work out manually your slope and your intercept, you do not have to do this in the assignment, okay? You can absolutely go work out your slope and your intercept with the regression tool in the data analysis, and you're going to say marks equals what your slope and intercept is. So you're going to write out that thing. So you're going to say marks equals your slope, so times your hours studied by exam plus the slope plus exams taken plus your intercept, like they've got it here. But you're going to give the actual values that you have calculated for 5 marks. Then they're going to give you this output, which is basically the output of that. Oh my word, do they give you the answers? No, thank goodness they've taken them out. They're going to give you an output and they're going to ask you, okay, in this output, what is A? Give the values of A and give the values of B. So work out the slope and the intercept. And for C, you're going to work out the p-value, which Gareth will show you how to do, or you can actually just pull it from your own solver. Okay, so just work that out and show it. Then for question 2.4, discuss the key assumptions of the multilinear regression. Comment on how well the model satisfied these assumptions based on the residual plots. So what we're going to have to say is, what is the key assumptions of multiple linear regression? We accept that to be linearity, and we accept that we will be able to fit a line. Okay. Then it's going to ask you to look at your R squared, your R test, and say, interpret the adjusted R2 squared. So if you are over here, your R squared, and there's an adjusted R squared as well. So that is just saying, like for this model here, it's done pretty poofy. Hey, the R square is 45, which shouldn't be yours. Then you're going to say that actually we can only explain 45% of the variance in marks and results. So if that R squared is at 90%, we can say actually our model can explain 90% of the variance in marks based on hours studied and past exam papers done. So if you tell us how many hours we have studied and how many past examples you have done, we can, for 93% of the cases, actually predict your mark. But in the other case, if it's low, it's only like 42% of the cases where we're able to predict your mark. So they just want you to interpret that nicely and then to say, what does it mean? Is this a good model? I mean, if we have above 70% where we can actually correctly use that model to predict values, then it's a good model. But if we're sitting under 45%, your recommendation would be, look, don't use this model. It's really not great. Okay, so that's the adjusted R squared. What does it say about the model's explanatory power? Can the model explain what will happen to marks as hours studied and prep exam past papers increase? And to what degree can it do it? Then is the multilinear regression coefficient B statistically significant? You guys, you can actually pick it up in the table with the p-value, and if that p-value is less than 0.5, you can say yes, it is statistically significant or not. But Gareth will do a very detailed workshop on this with you guys. And then you're just going to use the model to make a prediction. It's going to tell you that you have a student that studied 5 hours and prepared 5 preparation exams. So, and the pass mark is 80, determine whether the student is expected to pass or fail the model. So you're going to plug it in and you're going to predict his pass mark and say he's predicted to pass or he's predicted to fail. And that is it. Then question 3 is K nearest neighbors. Hi, nogal with the iris. Okay. So they're going to ask you to build a K nearest neighbors model. It's going to give you a flower. It's going to ask you to work out the Euclidean distance between the test and the sample. And I mean, we've done that in Excel with Nadia, and I have many Excel spreadsheets that's actually in that drive that I have shared. And some of you have actually asked me questions going through those videos, showing me screenshots of my videos. Sort the trainings data by distance and identify the 3 nearest neighbors. Determine the most frequent class among the top 3 neighbors, like actually choose your prediction, and discuss how K5 might affect the prediction and model performance in general. So K versus 3, like I'm looking at the distance between 3 neighbors, and then K versus 5, I'm looking at the distance between myself and the 5 nearest neighbors. So work out on K3 and then go change your K to 5 and then see what the difference is and discuss and explain it. Then for that linear regression, they want a report where you're going to have to basically do the following. I almost left that out. I'm sorry, guys. Okay. Or do they want a report overall? Let's just go see where they want that report and what they want it for. I'm not nuts. There was a report. Question 2. So for question 2, submit a PDF report containing the following sections: executive summary. So an executive summary is a brief explanation of what's coming in the rest of the document. I actually have a template that I will upload for you guys to follow, but that template is for PDAN and quite long. You're going to cut it down quite short here. So in the executive summary, you're going to say the aim of this study is to use to predict the viability of using students' exam studies and number of past exam papers written to create a predictive model. Then you're going to have a results and interpretation section where you're going to say, well, here's the results that I found, and you're going to put all your outcomes there, your slope, your intercept, all of that. And then you're going to do conclusions and recommendations. So and in the results section, I want to see your whole output from the data analysis tool pack and unpack that output for me, where you're going to say, looking at this output, and that's your answers from the questions. Looking from that output, we have found the coefficients of the model, which is the slopes and intercepts, because there's 2 features. This is what the slopes and intercepts are. This is how the model does overall. This is its R2 and its MAE or MSE scores. This is what they look like and what they mean. And this is what it tells us overall how the body has done, how the model has done, and then just end off with your conclusion saying, because we have an R squared of 100%, we can categorically tell you that this model can describe all the variances, like how does Y change if the values for studies, so the pass likelihood of passing or the pass mark change if we change the little variables for hours studied and past exam papers. Does that mean that we can actually look at the values given for past exam papers and hours studied, and we can use that to predict 93% of the changes in Y because there is this upwards trend? Or can we only predict 45% of the changes in Y, which then means that this model isn't that great, and we conclude with it's not suitable for deployment and adoption? Or if it gets really nice scores, we will say it's suitable for deployment and adoption, and that you'll do in a PDF document. Are you guys okay? And I'm going to answer the questions now. Yes, you can get a video on question 1.4 for the bias and variance trade-off, Bianca. I'll happily make it for you tomorrow morning and upload it. There might already be one on YouTube. I'll check after class, and if it's already there, I'll just stick it into your WhatsApp group. Yeah, for the Anati, the rule is generally just reference like the reference police is on your shoulder, rather in-text reference than not. So rather over reference than don't reference. So I would in-text reference and have a reference list, even though it feels really weird for numeracy. Andren, your hands up.
Sorry. Hi, Serena. Can you hear me?
Yeah, I can hear you.
Perfect. Just a question regarding the submission, even though it's quite far from now. When it comes to submitting, is it going to be all 3 documents individually submitted?
Yeah, I'll upload all 3 documents to ARC. Don't zip, because then we have to unzip. Okay, so you upload just your 3 documents straight up to ARC. And then you guys label clearly. Okay, just label your stuff clearly so that people know what is where. So as a general rule, the easier you make the markers' life, the easier it is for them to give you marks. Don't make them go look for the answers. Be like, here is the answer. Be as descriptive and clear as you can. Are there any restrictions? No, there is absolutely not a single restriction on what material can be referenced. You can reference anything, websites, YouTube videos. I think someone was going to share the referencing guide, did they? Dominic, was that you? Were you going to share the referencing guide?
I shared the referencing guide on the WhatsApp group. I wasn't able to send it on the Teams chat. I can't send anything on the Teams chat,
Yeah,
so I
none of
was
us
able
can.
to I was able to send it on the WhatsApp group.
Okay, so just use that referencing guide and you guys will be absolutely fine. So just so you guys know, I will only mark your linear regression question. Someone else is going to mark the theory, and Nadia will mark your K and N question. So you'll have each person that taught you the section so that people don't expect differences, so that I know how I've taught you. Where is my brain? So I know that I've taught you linear regression in a certain way. I will also mark it in the same way. Okay. You guys, if you ask, if the question in your head, should I reference, pops up, just reference. Just save yourself the pain. Just reference. Have no feelings. Just reference. Okay. So question 3 is K and N. So if you've looked at a source to help you with K and N, which you guys should be looking at 1,000,000 tutorials. No one is stopping you. This is an assignment. It's not a closed book assessment. Watch YouTube videos, look at tutorials, just reference what you've looked at. Be upfront and clear, and you cannot go wrong. And now, having looked at that assignment, does it seem super difficult? Or is it stuff that you have done and that you should be fine to do in the assignment? Is that a nasty question to ask you guys? Currently, is it no, it's not stuff that you have done, or no, it doesn't look difficult? So, like giving me slight heart palpitations here. Okay, so that's literally it. It's really plain and straightforward. And remember that you still have, it doesn't look difficult at all. It's not difficult. And you still have enough time to do that. And you will have more tutorials of Nadia. And you're also allowed to ask Nadia to go through the assessment with you guys in detail in a tutorial. Gareth will do the P-tests and T-tests with you guys. Even though you don't technically need them to answer the questions, it's just good practice to really understand them and how they work and what we do with them and why we compare means. I'll definitely make you that video on the bias and variance trade-off. Yeah, and then GAMS will be handled week after next by Daryl. And then you've got all your stuff to do and submit your assignment. So no reason whatsoever to be stressed out. Okay. Is it okay with you guys if I upload that video for you for ridge and lasso regression, because it's literally 10 minutes, and the bias and variance trade-off, and that we start logistic regression tonight? Because that we've got 2 sessions for, but we have to be careful. Yeah, I'll absolutely uploaded, Kat, no problem. I'll upload that early tomorrow morning so that you have it. But if you're already freaking out, just go look on the WhatsApp group. I did share the YouTube link for all and I have short little recordings from last year, but after the class tonight, I'll also link those in individually where there's short 10-minute recordings where I do explain these in detail. I'll link them back in. It's always nice also to make a fresh one for you guys. All right. Are you ready to start with logistic regression? I'm waiting for like a roar of yes, we're ready. We'd like to do this.
Yes, Serena, let's do it.
Okay, thank you, Dominique. Let's go. Okay, so I've got brief slides and then a bit detailed slides later because feedback from last year was like it would have been better if I'd gone through the brief slides first and then through the detailed slides so they didn't want to slowly die. So let's look at the brief slides and what we are working with. Okay. So you guys, if you understand linear regression, you already understand a good portion of logistic regression. And if you understand linear regression and logistic regression, you actually understand neural networks. And if you understand logistic regression and linear regression, you also understand support vector machines. So linear regression is super important to understand, and logistic regression is super important to understand. And luckily, neither of those two are difficult, but they help you understand other models really, really nicely. Okay, so we're still working with that fish data set, and we're going to look at 2 data sets tonight because the fish is going to kick our butts a little bit, but you need to see what can happen. And then I've got another data set that we can easily look at. Like I said, it's important that you guys understand this. I'm not going to rush this because we could potentially go all the way to MLE tonight, but let's not do that to anybody. Okay, so this is where we actually want to use regression techniques to do classification. We know that we said in linear regression, actually regression is not for classification because we don't have discrete values. Okay, so we want to be able to give a fish's weight, and we need an algorithm to take that continuous physical measurement and give us a strict binary decision if it is a bream or a perch. And that's what makes logistic regression interesting, because we're actually using continuous data for our classification. So we are force fitting some stuff together here. Okay. So here's what we have. We have weights, and then we have perches and breams, and we want to be able to predict based on the weight, and this is what this data looks like, based on the weight if this is going to be a perch or a bream, but we actually can't draw a line because it's not going to work. We won't be able to get. So a standard linear equation like mx plus ba stretches to infinity. So they won't give us a fish or a bream. Okay, they don't understand binary boundaries like this one does. So instead of fitting a line, we want to fit an S. Okay, so we need a mathematical engine that bends the infinite line into a strictly bounded probability. So what does that mean? Our y can only ever be 1 or 0. Okay, it can either be 1, the positive class, yes, I am a bream, or 0, the negative class, I'm not a bream. The only other option is a perch. And then we have this S shape, and this is the classic shape of sigmoid. It makes this S shape. And between 0 and 1, there's 0.5. And it's like the guy that separates the two fishes here nicely for us. Do you guys see that? So anything that comes into sigmoid and comes out as less than 0.5 will be perch. Everything that comes out as more than 0.5 will be bream. And that's why we have to have this S shape for sigmoid. Okay. Let me go see if you guys are okay. So far, are you following what I'm saying? Is that line is not going to give us a prediction with this data. It's absolutely not going to work. We're actually only touching 2 data points. But if we fit a squiggle, or if we use the S, the sigmoid S, still with this linear data, we can very much do a classification. Are you guys okay with that? Do you want to throw up? Kat, your hands up.
I was just trying to figure out why would it be on a graph if there could only be two answers? Does that mean when it's curving that an answer can lie in between? Like why
Yeah.
would it, yeah.
So because we are kind of using linear data to do a classification, but yeah, the curve, we decide that 0.5, you guys will see that. That's a rule we make. So that curve over here, where we get that little cut in the middle here, separates the two classes for us. And we actually say lower than 0.5 is the one and higher than 0.5 is the other. It's a thing we did. So let me go through it and then ask me again if you don't understand. Okay, so we know how to compute a regression score. Like we know how to work out linear regression, our mx plus b, right? Where are you guys? I keep losing you. Are you guys okay with linear regression? No, man, don't vomit. Anarchy, it's going to be fine. Are you guys okay with linear regression where we say we can actually calculate now if we have the data, the linear data, we can calculate the slope and the intercept. We're okay with that. And we can then use that slope and intercept and work out the OLS score. We've done that in the previous class. So we're going to keep that. We're still going to do this. And this is partly answering your question. Now we've got this linear data and we want to force it into classification. So what we're going to do is we're going to shove it into a sigmoid function. Okay. So the steps that you have to remember, and we're going to look at more detail now afterwards and go through an example. The steps that you have to remember for logistic regression is the steps you're seeing on the screen here. We know we are actually working with linear data. It's not discrete data. The data we are dealing with is weight for a fish. It's continuous data. Let's not call it linear data. We know we're working with continuous data. Okay. So we are going to honor that continuous data and we're going to calculate the slope and the intercept. We're going to work that out. Then we're actually going to shove that into a sigmoid function, which is going to give us a probability. Then we want to see how, like a probability of it's 90% likely that it will be a bream, 20% likely that it will be, what's the other one? A perch. Then we're going to go say how far wrong were we? And then we're going to add up how wrong we were so that we can do the gradient descent thing to figure out how wrong we were. So let's look at step one, okay? Compute the regression score. So we're going to open this spreadsheet that I shared with you all on the Google Drive, and we're going to take a look at that. Some of this looks very familiar, right? We are literally going to go and say, can we please work out OLS? And in this case, I just cheated. I just worked out the slope and the intercept, which we know from the previous class. I'm going to use the slope and the intercept. I'm just going to calculate that, okay? And I'm going to shove that into a sigmoid function. So what does that mean? Okay, so we calculate that slope and the intercept. Then we've got, it's actually called your log odds, but we're not going to spare ourselves right now. We calculate the slope and the intercept. We shove it into sigmoid and we come out with what we need in the end. Okay. I'm going to jump into another presentation and come back to this one so I can show you guys how we get to this. Okay. What the heck is going on here? So I'm going to open this as my presentation. The other one's also mine, but I had Notebook LLM make a short presentation for us. So as with the other slides, we now know how multilinear regression works. Okay. However, we want to use that same continuous data to be able to figure out if it's a certain type of fish, or we want to figure out if someone is underweight or overweight. Okay. So we want to use classification using probability, and it can work with linear and discrete data, but we're going to use it with linear data now. Okay. So what does all of this mean? It means this. This is the sigmoid function, okay? Sigmoid is a mathematical function that we use that will only ever return 0 or 1, okay? So this is a sigmoid calculator. So if we look at this calculation, this is online. I've entered 2. We said, okay, calculate for me the sigmoid of 2. Here is the sigmoid function. It's 1 over 1 plus Euler's number to the power of x. Okay. The s of x, yes, is the sigmoid function of x. X in this case is 2. So x equals 2. Calculate the sigmoid function of 2. The sigmoid function of 2 is 1 over 1 plus Euler's number, which is 2.718. It's always 2.718. It's a magic math number. Just remember it as that, to the power of negative x. So if we plug it in, we're going to say, oh, so let's say S2 equals 1 over 1 plus E to the power of negative 2. Then we're going to say, what's that E? Well, that's Euler's number, and 2.718 is always Euler's number. So we're going to put in 1 plus Euler's number to the value of minus 2. We're going to work that out, what Euler's number to the value of negative 2 is, to the exponent of negative 2 is. It will give us this value. We'll add 1 to it. Then it's 1 over 1.13533 this way. We'll get a value of 0.88. It is higher than 0.5. We would then write this as a sigmoid plus 1. But this is how the sigmoid function works. It just does this repeatedly. Why is that interesting for us? So we're going to compute the regression score. We're going to convert it to probability by shoving it into the sigmoid function. We're going to look how far we went wrong. We're going to add everything we did wrong up to get our maximum wrong. And then we're going to use gradient descent. But what are we feeding that x? What is that x value? What value is this? Do you recognize this? What is this? So this is the sigmoid function, 100% the sigmoid function. But instead of just giving a number x, what are we shoving into that sigmoid function? Who can tell me? Where are you guys? What are we shoving into that sigmoid function? Yes, Curtly.
The linear regression.
We are shoving that linear regression straight in there. Yes, Curtly, you are correct. We're using quantitative data to find a categorical data point. Okay, so yes. So, and we're going to use the sigmoid function just to equate it for us into a particular category. 100%, not hard, you guys, not hard at all, because all we're going to do. So let's go look at an example. We know that y equals b0 plus b1 times x equals, it's the same as y equals mx plus b. Statistic notation, calculus notation. Okay, so let's look at an example, and then we're going to go look at that spreadsheet. Okay, so this is still the sigmoid function, just written out. That S is just written out. What does this mean here? No one freak out. Everybody breathes. This is still 100% the sigmoid function, but we're saying is, what is the probability that the outcome is 1 for y equals 1, the positive class? What is the chances that this fish is a bream, given as particular weights? So what is the probability that the outcome is 1 given an x value? It equals 1 over 1 plus Euler's number plus that linear equation. That's the coefficients we learned before. That's our input features. This is Euler's number. And the sigmoid function will weigh out for us a 1 or a 0. It's really that simple. It's not that hard to do. And then we have from continuous to discrete. So that's what it looks like. So let's assume we have an intercept of 4 and a coefficient of 0.1. And let's shove it in there. So we're going to do this. We're going to say, what is the probability of y equaling 1 if x equals 80? So now we give x a value. We are going to use sigmoid. So 1 over 1 plus Euler's number to the negative of the linear equation. What is this? This is your slope plus, your intercept plus your slope minus multiplied by your x. That's all it is. It's y equals mx plus b. We're putting it in there and we're giving that the negative value. So then we just work it out. So 1 over 1 plus Euler's number, which is going to be 0.1 times 80 comes out to 8. Minus 4 plus 8. Minus 4 plus 8 is minus 4. 1 over 1 is Euler's number to minus 4. It's going to give us this little number here. Then it's just going to say, okay, so what is this? Is all worked out. Euler's number to the power of minus 4 is going to give us 0.018. Let's finish the formula. So we have to get 1 divided by 1 plus the outcome of this. The outcome of this is 0.18. So what is the answer? The answer is 98.2%. It's 98.2% sure that at 80, this fish is a bream. That's simple and easy to do. And then we go say, if PY, if we come out with 0.5, classify it as admitted here was an exam example, but if it's higher than or equals to 0.5, it's 1, the positive class bream. If it's not, then it is 0, the negative class, not a bream. So let me just find you guys. Is this making sense? Do you want to throw up? Can we go look at an example in Excel? And then we'll go back to those other slides and look what the heck we were talking about there and slowly unpack this. Okay, so let's go look at an Excel example. Okay, so here we have done an example in Excel, but let's walk through this example nicely and then let's go do it together. So we have here our weight, our height, and our weight. Okay, so this is our X value, only one feature. The next example, I will do a multi feature example with you guys as well. But to start with, we always start with one feature for the sake of simplicity. So this is our one feature height, and we're going to use that to predict the weight. Okay, this you should recognize from the last class, but you also don't have to use that. So we just got the slope and the intercept by using the normal little data feature thingy. So how did we get that? We went.
Sorry, Serena.
Yeah.
Have you uploaded this on the drive yet?
Yeah, it is there. Dominic, can you not find it? Have I stuffed up?
I don't see it.
Give me 5 seconds. It's
No,
right.
it's there.
Oh, that's
It's
my
them.
own folders. What is it there?
It's them.
Is it there?
Yes.
Guys, you know. Okay, can you find it? Can somebody post the link for it in the chat and help a friend out? Just right click, just click on it and then just hoist the whole link in here. It should be on the drive. Let's go see. Now you're going to see how many small folders I have on my drive. Okay, hold on. Let me get there. So we are not going to judge what the inside of Serena's Google Drive looks like. Okay, we're going to let it go that I have multiple instances of the small folder and I'm not sure which one I'm working with. Okay, I think it's this one. Yes, it's this one. And then if you open SMAA 8411, if you go into Learning Unit 1, you will see Logistic Regression. And here is the spreadsheet that I am working with. Okay, I actually have to upload 2 more there. I've done a bit of stuff. But here is the spreadsheet I am working with. Can you all find it? Oh, you shared the link. Hey, okay. Right, everybody get that, dude? If there is data in here, because I forgot to delete it from the last class, just delete this 2 columns as data. Okay. All right. So how did we get this slope and intercept over here? All we did is we went to data, we went to data analysis, because we now know how to calculate this. You don't have to do it anymore. So we went and found regression. We clicked OK, and it will ask us for our Y input range. So we went and said, here is my Y input range. Oh, I only have one type of fish here. Never mind. Okay. And here is my X input range. And we would like to see this in an output range, which we're going to go select way over here out the way. And we're going to click on OK. And there is that slope and intercept that I'm working with. You see this? These 2 numbers? They are 100% the same as those 2. I just copied and pasted it over. Okay, and they're just upside down now, sorry. But, okay, let me do it nicely. Okay. So if we want to go say, what is our slope? Do you see that this is I just copied that? They're still exactly the same. And then I put Eula's number there for us, just so we have it. Okay. Are you guys all right? You find you? Yeah.
Serena, Tabiso, yeah. Can you just go back to how you have done that regression table on the right? If you can just repeat it.
This thingy.
Or,
Yeah,
or even if you don't repeat it, I just want to ask a question around the data analysis.
yeah.
There were some
We're gonna
four
have to
options
delete.
that were there were some four options that were given to us.
Yeah.
When you were doing that, you can just repeat it quickly. Sorry.
Let's
Sorry,
go
guys.
do it. Let me just clean up my haha here. Okay, let's go do it. We'll do it one more time. Remember, you guys, we're not rushing. We're going to go nice and slow because we have 2 whole classes for logistic regression. So what you're going to do is you're going to go to, remember, if you don't have this, if you click here and you don't see data analysis or the solver, and we're actually going to need both for logistic regression. If you don't see them, you're going to click on File. You're going to go to Options. And you're going to click on Add-ins. Okay, then you're going to not click here because nobody knows why that is there. Then you're going to go to Manage Add-ins. Make sure it's Manage Excel Add-ins. Click on Go. You're going to say, I want the Analysis Tool Pack and I want the Solver. These 2. Okay, then you click on OK. Then if you go click on Data, they should appear here. Okay, then they are both there. Are you guys okay? Did that help?
Yeah, I understand that part. Sorry, I just wanted you to go back to where you select the Y and the X.
Yeah, let's go do
and
it.
then you select the range where you're going to put your output. So there were 4 options that were given to us at the bottom of that data analysis. So I just want us to get to that four options. The 4 options at the bottom there.
Yeah, let's go do them.
I think the question that I asked on the previous session was that when you were going through this calculation, we're trying to find the best line that fits the regression, right? So if you go activate, if you go okay, and then you activate after choosing your Y and the X, and you activate the I just want to see it again. You activate the line.
So let's go do that. Get that.
Yeah, the line fit plots. Yes.
Yes. So, I'll show you what. Let me help you with that. So let's go say, okay, let's get our Y range, and our Y range is weight. You're happy with this?
Yep. Yes.
And then it wants our X range. And in this case, we only have one feature. In the other example, we're going to have more than one. So we're going to select only one column there. But if more than one column makes up your X feature, you just select more than one column. Then accept the confidence interval of 95. Don't fiddle with these. Okay. Then there is your output range. So you can choose a new worksheet and it will put it in a whole new worksheet. Okay. Or you can say output range, and you can go say, I would like to put it over here. And then you tell Excel, you put this data over here for me. And Excel will moan at you if the space isn't big enough.
Yeah. So the residuals, if you look at the residuals, there's line fit plots, right?
Yeah.
The last option. The last option.
Let's show all the plots for you.
Okay, that's fine. And if you go okay, then can we say?
Yeah, there's your line, there's your predicted and your Y's, but the only thing is that these are going to be ugly now. Okay, so they're going to, if you want to show the plots, it's better to show them. Oh, I've also adjusted your plot.
I'm interested on the line fit plot, actually. The other ones, I'm not really interested on them because I understand them, I think. So that line plots, would we say if we were doing a manual calculation of this regression, we should have come up with a line that is similar to the one that you are just playing around with now?
Yeah, you should come up with a line that is similar.
Okay.
All right, so let's leave this guy here. So, and then here is just, and we can actually go look at your residuals and stuff at a later stage if they all match, because it's always nice to double check yourself. But what we're after 4, told you guys, sorry about the language tonight. What we are looking for is our slope and our intercept, which we've got, and we can verify that these 2 numbers that we have here is correct, so that I've copied them over correctly. And I've just put, I've just put Euler's number there for you because we're going to need it. And I've just not done, like I've stopped. I've rounded till 2. I haven't Euler's numbered to the value 9,555,000. And I left these here so you guys can remember that you can manually calculate this, but you don't need to. Okay. So let's go then and do our OLS. And our OLS tells us y equal m. And you guys, like I said, you have to check me tonight. Okay, like there I already stuffed up. Okay, now I was right. Y equals m. And we're just going to make that an absolute value or an absolute reference times x plus b. And that must be our absolute reference. Okay. Then we're going to get our OLS score. And we can take this guy all the way down. Okay. So if you're going to read up on this, but I think we'll get to that in the next class. Now, so let's not even break people. So we've got OLS. We've done that. We are here. We have gone and done this. We have worked out this bit. Now we want to feed that to sigmoid, okay, because we want to get a probability of a 0 or a 1. So we want to feed that to sigmoid. So all you do is you use the sigmoid function. Okay, so if you're going to look, and then I also had the people create, we can make our own formula as well if we want to, but let's go use the built-in formula first. Okay, so let's look at the sigmoid function. The sigmoid function is 1 divided by 1 plus, and this is the built-in EXP, this is the built-in sigmoid function that will use Euler's number, but we can also go do it manually. Okay, so let's, or do you guys want to do our manual one first, where we say, and let's just look at this, 1 divided by 1, 1 divided 1, plus, what is in SP20? It's Euler's number. Euler's number to the power of, and this is the outcome of our regression score. So let's go do our own formula and then compare it with the Excel formula if we're doing it right. Okay, so what should we say? What is the sigmoid function? The sigmoid function, sorry, the sigmoid function is 1 divided by, oh, did I use brackets? Like I said, I'm going to be a bit slow tonight, yeah. Okay, 1 divided by 1 plus Euler's number. Okay, oh, I didn't put the equal sign. 1 plus Euler's number. That needs to be an absolute reference, okay? And what are we doing with that Euler's number? That Euler's number is then also subtracted from, that I think this also needs to be in brackets. I'm going to go double check that formula. I think I stuck it in the bottom here for us. No, we don't even. They just go in brackets. Euler's number, okay, minus. And then the power of, and this has to be negative. Yeah, that is negative. The power of, the negative power of the regression score. That dude. Okay. Close the bracket and oops, yes. It should work it out for us. I think that is wrong. Let me go see what I have done wrong. Hold on. Let me just go get my formula from over here. Oh, nope. Oh, because I got the minus in the wrong place. Sorry, like I said, you guys kind of have to check me a little bit tonight. I'm not quite so like it myself.
Breathe, Serena, breathe.
Hey, you know what? I'm on lots of pain, like headache painkillers. But we can do this. Okay, so here is our own formula. So let's do it correctly. So it is 1 divided by 1 plus Euler's number. So let's just do our equal sign here and fix this guy up. Euler's number. There is our Euler's number. To the power of negative our regression score. Okay. And that will give us our probability. And then we can go do that. We can put this in to do that for you. But then if we drag this down, that's the built-in formula. Okay, that's not the built-in formula. It's even in the wrong place. That's the manual formula. That's us doing it manually. Okay, knowing exactly how that formula works. What have I broken? Something I didn't make the right thing. Euler's number is not a absolute reference. Okay, but let's just fix this and make this our formula. Let's go fix this. Okay, and we'll go come fix all the values so it's right again. Okay, it just changed because Excel picks up if we copy and paste stuff. So it should be 1 divided by Euler's number, and then this is our regression score. Okay, so that is 1 divided by 1 plus Euler's number to the power of negative our regression score. Is everybody with me so far with me clicking on 9 million places? Are you guys okay? Do you see it? Do you see we've done that manual calculation? Does it make sense? And do you see that we came out at a value of 0.5? So if we did this right, why is this now the wrong color? Let's go find the pink. We can drag this down and not break more things. And these are all breams. Oh no, those are purchase. But there we go. We can go and get that indication of what this is. And this is a data set that we have to apply gradient descent to. This is our first initial, often very wrong guess. Okay, so that's if we calculate this manually. You don't have to calculate this bit manually. There is actually an Excel formula that does this. Okay, this is what that Excel formula looks like. It's the EXP formula. So let's go take this dude and let's stick him in here. So the built-in formula is 1 divided by 1 plus, to do the multiplication by Euler's, to do the whole Euler's number times the negative value, it's just the EXP function in Excel. Okay. So, okay, so returns E raised to a power of a given number. That E is Euler's number. This formula knows to use Euler's number. That's why it does it for you. Okay, so you don't have to manually do it. There's also nothing wrong with manually doing it. Oh, what have I broken now? Why are you upset? So let's just do it the right way. We're going to say this equals 1 divided by 1 plus, and then it should be EXP, if I'm right, negative our regression score. Nope, I've stuffed that one up. Let's just go see. This should be in brackets.
Oh, is that power inside the EXP?
Yes, it's inside the EXP. The EXP function, if we get the definition, let's go type them for you guys. Ach nee, man. Let's type them here again. If we say equals EXP, not exact EXP, returns E raised, Euler's number, raised to the power of a given number. And we give it this number. If we go look at that formula, we say, please take negative the regression score. And you'll see that we are, this one has got more decimal points, but we are pretty much spot on.
Oh, Serena, also, when you highlight the square or the block, you can just double click the green thing and it will pre-fill the whole list.
Listen, you're going to show me that slowly.
So go back to just having the row 3 as the answer. You see that tiny little green square?
Oh,
double click that.
That's very nice, thank you.
Sorry,
nice one, kid.
It was annoying me.
I saw it so many times.
Oh, no, that's super nice. I didn't know you could do that. Thank you. Okay. So, and then we could do this, where we can say, but now I just, like I said, you guys, my faculties aren't so lucky here today, but I've done it for you in the introduction. Oh man, where is the one where but basically what you then want to go say is you just want to go do an if function in Excel where you want, if you wanted to say classes, that show the classes, but this is going to be totally wrong because with logistic regression, we actually have to do quite a few iterations of, and we'll see that you actually have to do quite a few iterations of MLE. So remember when we spoke about gradient descent. So I'm going to go back to the other slides that I was showing you, because these slides of mine, we will go through them tomorrow night, but this is what I'm scared about. The next section is for understanding. Do not freak out. It explains to you how we end up with sigmoid in lots of calculations detail, but we're not ready for that. Okay, so we will get there, but let's just go look at this simple guy. What are we looking at? Okay, right? We want to use the sigmoid function. We want to say, I want to shove in a fish's weight. I need you to tell me if it's a bream or a perch. And I want to use continuous data. So I know the line isn't going to work. So I'm going to take that line and I'm going to whack it into sigmoid. Okay. So here is something important to note, that standard linear equations, mx plus b, stretch to infinity. That answer, the outcome of mx plus b, can be infinite, both on the negative or positive side. They don't understand binary boundaries. And if we want to do a binary classification, we can't have infinite values. So we need an engine that makes that infinite values bounded. And that's why we shove it into sigmoid, because it doesn't matter what number we whack into sigmoid, it will fit it into that curve and we'll get that 0 or a 1, as we saw over here. Okay. Right. So we compute the regression score. You see, we get that Z value. We convert it to a probability. We whack it into our sigmoid function. This is where we calculate how wrong we were. Remember that in normal linear regression, we took the residuals. We wanted to see how far off are we. So the log likelihood is to show us how far we were off, and we add all of that to get our maximum likelihood estimate, our MLE. And that is the cost function, like the MSE or the R2 that we work with linear regression. We use MLE in logistic regression, and we're actually going to, you guys breathe, we will go work out MLE manually. We will work out MLE not manually. We'll do all the things. You'll understand all the calculations. We just have to build to it. Okay, so we can understand. And we're going to get there. Just breathe. So what they tell you is go and calculate your regression score. We know how to do this. Then this is unbounded, infinity. Okay, to make linear regression work for binary classification, we must invent this mathematical bridge that can translate bounded probabilities into unbounded linear numbers. Bounded is between 0 and 1. So we take that linear thing and we just whack it into sigmoid. Okay, so then if we go look, if you start reading up about sigmoid, which you guys will do, stuff is going to come up and it's going to say, well, we use the word probability, but actually sigmoid uses odds. And then why does it use odds? And what is all of this? Now, I need you to listen to me very carefully, okay? For us to shove numbers into things, and we want to see all of this linear range that we have. If we just use probability, the probability is the chance of an event happening. Odds is the ratio of probability. So if it is 1 in 3, odds is there's a 1 in 3 chance, there's a 4 to 1 chance. Probability is an 80% chance, okay? Probability only exists between 0 and 1. So if we just worked with probability, we would lose that infinity thing. So if we break away from probability, because you can only have a probability between it is not probable 0 or it's 100% probable, okay? A percentage, 0 and 1 or 0 and 100%. But you can have a 1 in 1,059 million chance of doing something. Odds give us more, like a broader area to work with. Okay. So odds is it allows us to work with a longer linear range. So if we want to shove a linear function into sigmoid, we're actually working with the odds. And this is just for understanding. You don't have to calculate it here. Your work is done. You are finito. You have passed your assignment. If you can do this, breathe. I've passed SMAA, no problem. This is so that you are understanding why things happen. Because what will happen is you'll see things like this. Just breathe. Let me find it. Where did I put it? Did I put it in your sheets, in your Excel sheets? Somewhere I put this thing for you guys to see. When you calculate the steps for Excel, did I lose my steps for Excel? It's going to give you a very definite, I just saw it. Have I been drinking my socks? It's going to give you very definite steps, and it's going to tell you, calculate the log odds. And then you're going to be like, what in the actual hell is the log odds? It's just the regression score. But all they want you to understand is they're not going to use the word probability, because probability is only 0 and 1. And we have values here that is below 0 somewhere. But that we don't, but you can get values here that are below 0, which then makes it very, very difficult to use these kind of things. So all they mean when they say find the log odds is they mean work out the regression score. Okay, and shove that into sigmoid. And then they're trying to tell you in great detail, why did we use the log odds? It's simple. Probability goes from 0 to 1. Okay. Odds allows us to go from 0 to positive infinity. But we should be able to use the values of a fish from negative. Okay, so a fish is a bad example, but we should be able to use values. This regression score should be able to be a value from negative infinity to positive infinity. Does this change your life? No. Is this jargon you need to know? Yes. So we say if we use just probability, we couldn't go more than 100. Okay. If we use odds, we can go more than positive 100. If we use log odds, we can go all over. So when you hear they talk about, oh, it's the log odds and all of that, you literally just work out the equation of a line. And that value will be anywhere between negative, can come out anywhere between negative infinity, and you whack that into the sigmoid function. The reason we can handle anything from negative infinity to positive infinity is because sigmoid, the formula itself, can use log odds. Okay. You don't have to calculate it, nothing like that. Here is what we've just done. That's all it does. It says if you want to use linear stuff, this is why we use sigmoid. This is why we shove it into sigmoid, because it does that log odds for us. Okay. Does this make sense? 54.6% confidence, y equals 1. And then we're going to talk about the cost function in the next 10 minutes. I need to check how much you want to vomit. Yes, if we could just, yeah. The regression score is the OLS, Tumelu. It's just, but what they do in machine learning is now they're not going to refer to it as OLS, they're going to refer to it as the log odds. But it is 100% just working out the best possible line and shoving that into sigmoid. Yes, Kat, ask me your question.
Sorry, I may have gotten my brain fumbled in what you were saying just now, but I just want to clarify if we're going to use odds because you can use the values of infinite, beyond the 1 and 0, why don't you still use probability for sigmoid, because it's still within that realm of and before 1 and 0, even if it's infinitely negative or positive, because it doesn't infinitely go up, it infinitely goes horizontal, because it will never touch 1 or 0.
Because we need to bring it back to a classification. So what this is all about, and where you're going to start reading up this stuff, is explaining why we use sigmoid. So sigmoid can ingest, we can throw into this filter a number from infinite negative numbers and infinite positive numbers, and it will whack out a 0 and a 1. So we always want to get back to a 0 and a 1. So we could have stopped the class right here and you guys would have been fine and been like, oh yeah, I just whack it in there. But when you start reading more on the internet, you're going to see stuff like it's going to say calculate the log odds. And you're going to be like, why? And what the hell? We just did OLS. So you want to calculate OLS, and in logistic regression, OLS is known as the log odds because it is a number all the way from negative infinity to positive infinity that we can shove into sigmoid, which will then give us a neat classification that we want in machine learning, and it will give us a value between 0.5 and 1. So it will be either lower than 0.5, negative class, it's not the fish we're looking for, higher than 0.5, positive class. That's what all of that means. Did that make sense?
I hate to paraphrase, so it
No,
is.
you can paraphrase.
So that linear equation, like by predicting log odds, like the Sigmund Freud function converts those infinite log odds to either a 0 or 1 clean.
100%.
Okay, that's starting to make sense.
That's all it does. And that's what we've done here, is we've calculated, this could have come out to any number. We've calculated that, we've shoved it into sigmoid, and it gives us a value between 0 and 1. And we say that cut off at 0.5 because of the sigmoid shape is how we separate between. So we could have then, but I can't remember the if, like, let's say, so we could now have said if value, if true, this is greater than or equals to 0.5, then we're going to say it's 1. Because that's a positive class. Else, we're going to say 2. And then there's our prediction. So if we go back to these, we've basically done this. We've gone and said, okay, I want to use logistic regression very much with linear data. I need to use sigmoid. Oh, here's the thing that I was looking for. So here it says compute regression score. If you're going to look at tutorials, it's going to say compute log odds, okay, because it's that number that can range for anywhere. And the horrible thing is that when you ask them why is it called log odds, they're going to say it's mathematically convenient. That is my favorite statement in math. So I was going to say it's serenely convenient. Like, why do you want to park there? It's serenely convenient. It's mathematically convenient because it actually means the same thing. So the steps to conduct logistic regression is compute the regression store, convert it to probability. So that's your log odds, shove it into that probability. Then go find your mistake and add up all your mistakes. Find out how wrong I was and add up how wrong I was. And we're going to do that as well tonight. And then we're going to look at a few different examples. And then we're going to stop because I don't want to kill you. But in these slides, which I will go through with you, I mathematically explain to you how do we get there. So what will happen is it will say, why don't we just use linear regression for classification? It doesn't work well because it can output values outside of 0 and 1. It fixes this by using sigmoid to give us the values between 0 and 1. Okay. So there's the sigmoid function. We are now comfortable with that. Then it's going to come with odds and log it and log odds. And you're going to be like, what in the actual hell just happened to me? And this is just mathematically showing you why we ended up using sigmoid and the odds and log odds. And here it is. Logistic regression models the relationship between independent variables x and a binary outcome. Since probabilities are bounded between 0 and 1, directly using them in a linear model won't work well. Instead, logistic regression performs probabilities into log odds, which make the models linear and more mathematically convenient. So, can't use probability directly, so we go work out and this is just an example how odds are worked out. We go work out our regression score. We shove that into sigmoid. We get our output. It converts it back to a probability. Why? It ensures linearity. It removes the probability bounds, and it allows for easy implementation because it is statistically and mathematically convenient. So what you have to remember is the more you go read about this stuff, the reason I say the log odds is just because that linear equation will have a value from negative infinity to positive infinity, and like Kat very nicely said, then sigmoid will just shove that value for us into a value between 0 and 1, which we'll use for our classification. All right, are you guys okay? Do you still want to throw up? So Mandla, one small problem is I can't get onto ARC. Unfortunately, something is wrong with my user account, and EMERIS is working furiously to try and fix it. I can't get into ARC, neither can Nadia. So all of these documents are on a Google Drive. Will somebody share the links with the Google Drive with Mandla, please? If you ever want to know if you should take 2 GenPrain and a Panado, the answer is no. Just, can anybody share the Drive link with Mandla? Kat, your hand is up.
And I want to ask, if we use, I imagine this is applied on risk models. So if we use this on like a credit card to see whether or not fraud is occurring, how would they use that? Like, is it if it's a negative, then there's a less, and then you plug that negative linear regression into the system, it will give you like let's say like you buy a coffee 1 kilometer away from your house.
Yeah.
And then it will give you just a negative number like -9. But then if you buy a diamond watch like 100,000 kilometers away from your house, it can give you like a huge positive number. I'm saying, is that the linear part? And then if you shove that in sigmoid, would that change it to whether or not you're most likely probable of fraud or not? I don't know if I'm making sense.
No, you're making 100% sense. That's a really good example. We're actually going to go look at a loan approval data set quickly, go work that out in a loan approval data set. So we're going to look at how it looks like, because we've now looked at fish, but the problem with the bream is that the data set is too perfect, and you're going to see, and we're going to talk about the log likelihood and the solver a little bit. But I've uploaded for you guys the loan approval logistic data set. Quickly download that. So let's go practice on this data set and what happens, and have a look. So we have an income, we have a credit score, we have a loan amount that they've asked for, and we have a debt ratio, and we have some examples if the loan was approved or not, and we can have a good look at this data as well. So we're going to go quickly do 1, 2, 3 logistic regression on this clean spreadsheet. We of course have the other spreadsheet to look around for formulas, but we're going to go work this out on a clean sheet so that you guys can practice. But the logistic regression is only in assignment 2. Okay, so get this sheet down, let's go practice, and then we'll move forward. Right. And then remember, your assignment literally stops at like what we're about to do. But what I need to do is teach you well. I don't want you to go talk to a statistician one day and he's going to go like, did you work out the log odds? And you're going to be like, what the hell are you talking about? I need you to know what you're doing, not just do stuff. Okay, so let me know. Show me a thumbs up when we're ready to start with this dude. Or do you guys want me to give you, okay, do you want to do it together? And then I've also got a student one that I'm going to upload for you to do by yourself. So let's do this. Let's go work out some stuff. Okay, so let's start and say, well, we know we need the regression score, but its real name.
Serena, where can we find this?
Oh, I've just uploaded it to this,
Oh, okay, I see it. Yeah, I see it.
Okay, I'm going to find the words again tomorrow. Sorry, guys, that I'm stuttery. And I will also, there is a video from last year where I don't sound like this. Okay, right. So let's do this. So we're going to go work out the log odds, which we now know is the regression score, or OLS, or whatever YMXB thingy, whatever you want to call it, so you remember. So we're going to go do this quickly. All right, so we're going to go work out this guy. That's quite a long thing. So let's go work that out. And to do it from scratch, we're going to say, and this is now multi-feature, né? But we get to be nice and lazy. So we get to click on data to say we want data analysis. We want regression. We're going to click OK. So our Y input range in this instance is if the loan was approved. Yes, like this bank is not nice to people. Hey, they're not approving many loans here. If the loan was approved, okay, our input range is what was this based on? It was based on the income, credit score, loan amount, and debt ratio. And Kat, here you'll see those things like where the debt ratio is high, they're not giving you a loan. And when the debt ratio is nice and low, you're getting the loan. Okay.
Also,
Yeah.
Serena, after the lesson, I can show you how to do that part quick as well. What you just
Yes.
did.
My slow highlighting.
Yeah, you can do it in like half a second.
Listen, always ready to learn more. Okay,
Awesome.
so let's whack this in here. If you guys have tricks, remember what I said, we must share. Okay, because I literally, oh, now I forgot to take that out. I literally only use Excel when I teach stats, eh? Everything else is in Python. We do this so that we understand. So if you have cool Excel tips, especially if they could make my everyday Excel nightmares much easier. So let's remember how we're going to do this. In the previous example, we had one feature, but we now know how to do this for multiple features. We are going to say equals X times and M. And we're going to like that. And we're going to say next one times its slope. Like I said, guys, please check my stuff tonight. This one. And check that I'm not making boo-boos up there. Times its slope. Plus this one times its slope plus the intercept. Okay. Gotcha. And there we're hitting negative numbers. Do you see this?
Got it.
Okay, that's false. All right. Okay. So, and do you guys see here the predicted Y here and the predicted Y here is the same? There's some stuff to work with. If this happens, why did that happen? What have I stuffed up? Let's just check quickly what I have said. I have said A2 times. I'll check my formula. Oh, yes, I have stuffed up. Nobody's watching me. So it is income times income slope, not the intercept. Make that an absolute value plus credit score times credit course, that thing, make it an absolute value plus loan amount times loan amount slope, make that an absolute value plus debt ratio times debt ratio slope, make that an absolute.
Network?
Was probably.
Probably.
Oops.
Yeah.
No idea what just happened.
Hmm.
Am I back? Can you guys see me?
Screen's loading.
Yeah.
Yes, we can.
Yes, we can now.
Yes.
Yeah, Angarthen, what just happened, hey? It's a sign. Should have cancelled tonight's class and gone to bed. Okay.
Double click. No, double click.
Ah!
Save your time.
Okay.
There we go.
Okay. So next we're going to say we're going to shove it through sigmoid. So do you guys think you can do the assignment, or do you think you're going to really struggle? And sigmoid equals 1 divided by brackets 1 plus exp negative that. Yeah, sure. How are we going to be okay? How are you guys going to pass this course? Ah!
There we go.
Breathe.
How are you guys going to pass this course? It's so difficult. It's so hard. So, and for assignment 2, you stop here, and then they give you values, one value to feed in here. So they're going to give you a line that you need to apply this to, because it's really I don't know why people make stats seem so complicated when it's actually so very simple. But there we've just done one from scratch. Okay. So we also can go because we're supposed to have class till for another half an hour. Hey, so let's talk about what's coming next, and then we'll do that in the next class. Okay, so we'll start working out our mistake in the next class, or do iteration. So remember we spoke about gradient descent. Did I put it in these slides? Okay. So when you go look up logistic regression, and you're going to ask, how do we optimize it, or how do we make it better? Because remember, there should be multiple iterations of this. So what we do is we maximize the total likelihood. So the MLE, the maximum likelihood estimator, is how we can optimize this. So this was one guess, okay, or one iteration, but we now know from gradient descent, and we're going to talk about gradient descent now again a little bit, but we now know from gradient descent that we can actually tweak these values to get better and better. Okay, the good news is that you will do it with the solver. I'm not going to apply the solver now. That's for tomorrow or for the next class. But you can go say how many iterations we want to run, so we can actually practice some gradient descent. Okay, but tonight we're just going to talk about the cost function, and in the next class we'll apply the cost function. I see there is a hand up. Yes, James.
Okay, good evening, everyone.
Good evening, James.
Just with this example that we're looking at, I take it, I thought maybe we were going to get to interpret what it says. So from what I've been trying to follow, and unfortunately I didn't read this part of the course before we had the lesson, but I was quite following. But I was thinking now with this one, I was thinking everything above the 0.5 should have been a loan approved. And then everything below, for example, 0.5 should be disapproved. So are we saying in this case, this what can I say? It's not interpreting it as we would have thought, because it's actually giving more than 0.5, and all of these people's loans have been disapproved.
Let's look at this. That's an excellent question, and that leads me into the next part of the lesson. So let's go see what happens. So we are saying yes. If it's more than 0.5, the loan should be approved. But listen, this is going very wrong here. So let's go see. If sigmoid is greater than or equals to 0.5, then it should be loan approved. If not, it should be loan not approved. Okay, right. But now we're getting totally different values here. Do you guys see this? Or did I do this backwards now? I did it again. Hold on. So why are we getting this? Why are we getting this so wrong? Why? But there's some that will be right. Okay, but why is this looking so weird? What is going on here? So remember that we started with an initial slope and intercept. So how does this kind of stuff work, and what does those iterations have to do with it? So let me go find a whiteboard.
Is it because the model's guessing?
Yes, it is, because it's its first guess. It's taking an initial. So what am I looking for? Free whiteboard.
So you're saying the banks are guessing our credit scores? Rubbish.
No, the banks are doing a good job. But they are guessing.
Rubbish.
Okay, so this work? Okay. So we now want to go and choose if we're going to give this person a loan, and we want to use a machine learning model to decide this, okay? Why do we use machine learning models? And why did we bring Python into stats? Because Python can do things really quick, really fast, okay? So I'm going to draw this shape here again, and this shape always means, not always, in this class means gradient descent. So we want to get to a point where our error rate, which in this case is the log likelihood, where our error rate is as small as possible. Okay, so we have to start somewhere. And to tell you guys the truth, the example where we're using here, that we are using here to work out the slope and intercept is useful for you guys to understand the linear equation, but we could have actually also fed it 0, because in Python, what's going to happen is it will initially just either put in 0 and 0, or in our instance, we did work out an initial slope and intercept. So we come out with an initial M, and we come out with an initial B. This was 102, and this one was minus 900 something. I don't have the correct values. So this is the initial guess. We need to, through gradient descent, slightly tweak this over and over again until we get to the best chance. Okay, so we have a cost function or a penalty or something like this that we use here. And please don't freak out when you see this. Okay, it's a very simple formula. We will apply it in Excel. We'll do it in the next class. And we've done it here. This is our cost function. If I go back to these fishies, this is that cost function we have applied to figure out how far am I wrong? Okay, how far did I stuff up? Because this should be 1. So how far was I wrong? Then we total all of that together and we get a total log likelihood. Okay, then we want to use gradient descent to change it. So our first guesses, okay, our first thing we do is we go like, I want to work out all of these species. Okay, well, I want to take all of these customers and I want to see if I can give them a loan. Okay, so I go find out a slope and an intercept. Okay, and actually the slope and the intercept here was completely different because it was, I have multiple slopes and an intercept. So we have to change these guys. All right, so I need to be able to change these. So how do I do that? Okay, so I go do my first slope and intercept. I go and I say, tick, 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 tick. I do all my calculations. None of you, all of you gets a loan. Then we go and say, okay, how wrong was I? What was my actual Y value and how far am I off? And we're using log likelihood here to do it because it is the formula or the cost function associated with logistic regression. Okay, however, if you put a minus in front of it, it's binary cross entropy. It's a very well-known penalty cost function way to optimize things in machine learning. So we go like, all right, oh my word, we were very wrong. Okay, so we have to change this dude a lot. So here we are, look how wrong we were for, let's look at this. I mean, we're way off. The loan wasn't approved. We're approving a lot of loans here. Why are we doing that? So then we go and we say, okay, if I was very wrong, I'm going to make a big change. And I go make this 200 and minus 1,800. These are just random examples, not real math numbers. Then I go do all my calculations. I work out my log odds, or we don't know my OLS, my MX plus B thingy. We work it out. We shove it in segment. We get a value. We go like, we work out the log likelihood at the end, which we'll do in the next class, our cost function. How wrong was I? Oh, I'm still pretty wrong, but it's not that bad. Then I go and adjust these guys again and again and again. Oh, my goodness. And again and again, until we get to the point where the adjustments only make us sway a little bit here in the bottom. The changes are so minute that it makes no impact. If I change it this way, really doesn't change much. If I change it that way, it does. And then that model has converged. I found the best possible value. And then we actually will have better outcomes here because as these values change, that will change. So I'm going to show you a quick example of what I mean. Oh, do I have the mental faculties to actually work out log likelihood in my space now? Let me not break you guys. But basically what we would do is I'm going to show you an example here, what we do. Okay. is we will apply the solver. So we will say, we will go work out our log likelihood, okay? And I've put the log likelihood guy already in for you. So it is y times the log of the sigmoid plus 1 minus y times the log of 1 minus the sigmoid. That's the formula that we get here. Okay, so if we look here, that is our y value, okay, times the log of h3 is this dude over here. And what is that? It is using the output of that sigmoid, okay? Plus 1 minus C3, 1 minus y again, times the log of 1 minus this sigmoid. It gives us this output. And we'll talk about all of that in the next class. We add that all together. And that gives us totally how wrong we were. And we can see we're working out how wrong we were because we're working with our actual y value. Then we go like, I actually want to fix this. So we can do something like apply a solver. So I'm just going to take this guy and make a copy. So we can say, okay, so fix this for us. Apply the solver. So we can then say, okay, let's apply the solver. And the solver will say, set to objective. This is how wrong I was. Okay. Please change these two values. Please change the slope and intercept. Then I'm just going to say solve once. Oh, sorry. This is my bad. Hold on. That's just me. Now it's going to go nuts. It is this value. Then by changing these values. Okay. And then we're going to say solve. And the solver is going to run into an error here, which I'll explain in the next class, which is why this data set isn't great, but it will change the slope and intercept to find the best possible slope and intercept. Okay, and the solver's error it's running in here is it's finding zeros, and I'm going to explain that in the next class. It's never going to happen in the data sets they give you for the assessment, but it will happen in your life. And then how do we fix it, which is clipping. But I will explain all of this to you guys, like when we clip and how we clip. I have a clipping example in here. We'll talk about that in the next class. But that is how this works, because we can literally tell that solver to do this 500 times, 5,000 times, because we can say, do it 9 million times. How many times do I want this to happen? Okay. And then when it finds the best possible slope and intercept to make this debacle, and we're actually going to apply this in class, in the next class, we're going to apply the solver, we're going to change this, and then we're going to go see how this changes, and we're going to work out our overall score, and we'll see how multiple iterations of going like, this is my first guesstimate based off these guys. 500 times that we've adjusted that slope and intercept, we will end up with the best possible sigmoid output, which should give us a really good score. Does that make sense, or do you still want to throw up? Kat, your hands up. Tabisa, your hands up.
Can you, Tabisa, go first because I'm hijacking this class.
Okay, Tabisa, let's hit it. What's up?
No, you're not hijacking, Kate. We're there already. If you can go back to that loan spreadsheet, I'm a little bit confused here.
Yeah.
If I look at that spreadsheet, you already said on the loan approved 0 and 1, which I guess it is approved or not approved, right? On what basis was that loan approved or not approved, and what would the last column, the column H, help with this? Is it just a model that it has to be learned by the algorithms to find the best possible features that will approve or perhaps maybe disapprove any of this loan, for lack of better word, disapprove or reject, actually.
Yeah.
Can I try to answer just to see if I understand?
Okay.
You see that column H, if you go back to that drawing you were doing?
My beautiful drawing.
Yes. That column H is a single point on that curve.
Yeah, it's here.
It's
Okay.
a tooth. So every time you run the model, you're supposed to go as close as you can to the bottom, and the bottom is the cleanest separation between 0 and 1. Am I understanding that correctly?
100%, yeah.
Yes. Oh my gosh.
Okay, so what he was saying is that we want to separate between what we have here, but remember, guys, this is just random data. I think I just had this generated. But what we have here is we have supervised learning. So we have an example here that for a person with an income of 32,000 Rand a month, a credit score of 553, I didn't work, I know what none of this means, who wants to learn 34,000 Rand with a debt ratio of 0.1, he didn't get the loan. This is the real data. Okay, that we got from the bank. So if you guys want to give me any domain specific stuff to work with, it will help you understand. Like, go take an example at work. So let's look at this one. Let's do the student one. Let's do one more. And this is this one I've already applied the solver. Okay, but let's just go here. Let's do this. Have I applied the solver to all of them? Let's go do the student one. So this one says, will a student pass the exam? Okay, so let's go put a chart in here. So let's go see what this data looks like. And then I will come for Excel tips. Don't you guys worry. And no, I want the right one. I don't want this one. Okay, I do not have the faculties tonight to sickle with Excel charts. I want them all in one. Okay, let's not do that. We'll do that in the next class when I have my faculties together. But let's look at this student. Okay, let's look at individual students. Okay, he studied 7 hours. He attended 90% of his lectures and he slept 8 hours. So yeah, he passed the exam. This one over here slept 3 hours. He studied 71 hours and he slept 8 hours. He didn't get it. So we can also see, like, we can work out correlations and all of this to see. All right. So it seems to be like, he attended. It seems to be like attendance is our biggest dude here that makes. This one studied 0.4 hours. His attendance is 70%. He slept 5 hours. He didn't make it. So we can see that there's correlations here. Okay, and we can go work out those correlations as well to say if there's positive or negative correlations. All right, so we can basically see a student obviously should sleep more and attend more and study more, then they'll pass the exam. So let's go do this example. Okay, so let's go say, okay, let's go do our first initial iteration. So we know these guys passed. Okay, these guys didn't pass. And if you look at it, the guys that didn't pass, the hours studied is generally low. I'm just eyeballing this. Okay, right. So let's go say, okay, we would like to do this. So we are going to make our lives very easy. We are going to go to data. We're going to go to data analysis, regression. What do we want to say? What is our Y input range? Well, it's this. Does it work the same for this? No. Okay. What is our X input range? It is this. So I'm just going to not show all the plots this time. Okay, so where would we like to see this data? Yeah, over there is perfectly fine. Okay, whack in that data for us. Then we can go say, let's go work out the OLS. And that equals that one times that one plus that one times that one.
Yeah, maybe we can take over the class. I see you understanding this much better.
No, dude. I was just really good at maths in high school, my guy. So like I when she's putting the graphs, I'm like, what the hell is going on? But when you're looking at equations, I'm like, oh, okay. Wait, did she answer your first question though? The first part of your question. Also wanted to know.
No, she didn't. I was hoping that from the example that she's doing now, she would actually get to your point that I was trying to get into. Or at least the question that I was asking.
Also, isn't this the stuff actuarial scientists do? Why are we doing this?
Man, I'm
I'm
just
confused.
going with the flow.
In the end, we will be using this. Like if you look at how we are doing our data analytics,
Yeah.
we have to almost learn the statistics part, which fits into the data analytics when we are creating algorithms. Oh, I think that's the end goal.
Data science and actuarial sciences intersect.
Oh, okay. Because I'm seeing risk calculation here, and I'm like, dude, not that good. Jeez, what's going on here?
Yeah, they intersect a lot, like predictive models and whatnot. Almost the same thing.
Do you guys have like an example of where the linear regression would be used? That one where it's infinite? Like, do you have a real life example of where it would be used?
Not from my side, man.
Because I don't know where that would be.
I would love to know that as well. I would love to see some examples.
Like not from my side as well, but then you see with the fish one.
Please talk about the fish. I'm lost.
Okay. Before she comes, okay, the fish one. The way I took it, let's say we have got two types of fish. For extreme cases, I'll take a normal bream and maybe a bigger fish, a shark, right? So first of all, we try and maybe use linear regression to say the weight of the fish and maybe the type of fish. So with the bream, we take the weight of the bream, and then we say what type of a fish is it, and then we discover that okay, the bream is basically a certain weight on average, maybe a grown-up one. And then we look at the weight.
Why my stupid laptop keeps doing this.
And James is showing me how to do this fish thing, Serena. Like, so
I was attempting, and then with the basically I was saying with the fish example, which was shown first at the beginning of the class. I'm saying giving examples of, let's say, a bream and maybe a shark, and then we're trying to say what's the weight of the breams, and then we've got average weight of maybe a grown bream, and then average weight of a grown shark. So we're saying now that's linear regression, trying to see what type of a fish is it. And then we've now discovered this is the similar size of a average size of a bream, and then this is the average size of a shark. Then we're saying, how can we get this information to be able to classify what type of a fish it is now using this this formula of the, what is it called again?
Sigmoid. Yeah.
Sigmoid. Right. So now you will find that if you put in the formula in a certain way, like now, where we're getting the errors, now you're trying to refine it so much that it can divide between and give you not exact, but then it will likely give you to say if you put in the weight of a certain fish, you will be able to tell that this is a bream and this is a shark because of the different ways that they have and how you have used now this sigmoid to be able to tell them apart.
Then where does the infinity come in that example? Is it the infinite amount of weights that you can plug in? Or like what does... Oh, okay.
Yes,
Okay.
the range that you can put from the small bream to as big as a shark.
So you can get a
Yes.
negative
Yeah.
bream.
Yeah, so you can't, a bream is
You
not a
won't
great
get
example.
negative.
No, you won't get a negative bream, but remember that this isn't just for fish. This thing should work for everything in the world. And there are things with very high negative values that are valid values. So for an example, I can think about with negative values is I run a hydroponics tent in the desert in Donkerbos and Umaheke in Namibia, and it gets -10 there, and I need to be able to feed that data into a random let's say logistic regression, because we are classifying the state of that tent so that the heater comes on. So like a negative bream fish, okay, but that temperature definitely goes into a negative. So I need to be able to handle from values negative infinity to positive infinity. So remember that logistic regression must work for tents, fish, pencils, mermaids, unicorns, student scores, spam. It must work for anything you can really classify, although there are, I should go, we'll do that in machine learning. You do look at the data set and see which one is more suitable. But there we go. That's what it is. And that's exactly it. So we have this infinite range of stuff. And that's why we use the regression score, and we can get out to from -10 to +5,000. All of those values, we want to shove it into a formula which will give us a value between 0 and 1, which we use to classify which type of fish this is. So this is using linear data for and that's why it's called logistic regression. It is an instance where we use linear data to do a classification. And that's why this little thing here was important for you guys to see, that sigmoid probability is between 0.1, okay? Odds, if we worked with just probability, we would just have 0 and 1. If we worked with just odds, we would just have positive infinity. But we use with log odds because we allow negative infinity to positive infinity values to be shoved into. So synthesis, structure alignment to achieve log odds from negative infinity to positive infinity can now perfectly equal our linear equation, because mx plus b needs to be able to range from, oh no, I'm going to drink. I'm sharing the screen now. I don't
Clippies
know
and
what
Coke.
is.
Come on, Clippies and Coke.
Yeah, Clippies and Coke. Well, yeah, but there you go. That is why we need this. So we can have this linear equation that we can shove into sigmoid. And that linear equation needs to handle values from negative infinity to positive infinity. Now there is lots of hands up. Do you guys have questions? You can also ask James. He's done a good job. Do you have any other questions?
Bianca.
Bianca?
Hi, Serena. I just have a question regarding the loan data set.
Yes.
If we can just go back to it quickly.
Yeah.
I just want to confirm that, so we say in our OLS model, we take the X variable 1 times the income value in cell A2.
Yes.
But how do we know that X variable 1 relates to the income value in A2? Why can't we just say X variable 1 times the debt ratio? An example.
Okay, so in Excel, how Excel does it, and it's particular to Excel, is if you highlight all of them, it will work left to right. So the most left side column will be X variable 1. Then towards the right will be X variable 2. Towards the right will be X variable 3. Towards the right will be X variable 4. No, don't break stuff now, Serena. So that's in Excel, how you figure that out. It's always left to right if you've highlighted a whole block. Okay. However, if you do something like this, okay, if you do something like this, where you're going to say, let me just clean this. I'm a little bit OCD about this. It mustn't be there. Those lines, and they mustn't be there. And I know there's a clear formatting button. Somebody must also find me that. It's missing. Okay. What if we do something like this? Because you don't have to always use all of them. So if we had something like this, let's hope I don't stuff it up now. But if we have something like this, where you want to say, this is still our Y input range. Ooh, I left some nanas at there. Okay, but you can also do this, and you can say it's this column. I want to say you put a comma. I haven't done this in a long time. Comma, that column or that bit. Okay, now let's just do the whole column before we make Excel have a meltdown. It will be the first one you highlighted and then the second. Okay, I have to go remember how to do that. But if you're just using individual columns, it will be the first one you highlighted and then the second. That's how you know. Does that answer your question, Bianca? Am I sharing my screen?
Yeah, thank you so much, Rena.
No problem. Kuchle?
Sorry, it's Kat first.
Nah, you go first, dude. No, you go first.
Okay,
Okay.
Kuchle?
Thank you. So ma'am, I understand most of what you have said, right? I just have a question about cases where the data is not as easily differentiable. Wow, wrong word. Easily
Separatable.
Yeah, separatable, where like certain features in certain, say, fish, for example, they are blended together or overlapping. What would happen in that case? Would we use the same formulas, or would we find a different way to kind of classify the different fish?
So that is something that you guys will learn over time, but not all algorithms work for all data sets. So if you guys have had a look at your PDAN assignment, those of the people that are doing PDAN, the machine learning part is already up. But not all data sets is best suited to all algorithms. Logistic regression, though, is pretty suitable, but what will happen is you'll find the best variable. So let's take a look at this lone data set, which is like a bloody messy. So what we would do is we would go look for which one is most correlated to each other, and you'd use that one. So there's called feature engineering or feature selection. Like here, we just used everything, but we could have gone and said, we want to see the correlation between income Oh, that's not going to work here because this is classification. What am I doing? Okay. You would do the best feature selection to see which one is more correlated, which ones have more linear tendencies and stuff like that. So if the data is really messy, you have to go pick out the best ones. And then in Python, you'd show a scatter plot or a pair plot. You can also show them in Excel. I can show you guys in the next class. You choose the next one, but there is difference. So when the data is really messy, so there is also support vector machines that's used for classification, which has also lines of separation. So you will learn which data is best for which. So let's go ask this. Which ML algorithm would I use to classify if the classes are hard to separate? Then it will tell you which one would be the best to use. And like I said, it will be support vector machines because of how it works. Because there's a plethora of classification algorithms out there that you could use. So if in that case, maybe this is not the best algorithm, but the only way you're going to know is if you apply the algorithm, you get your score and it's a disaster, and you tweak the data and it's a disaster, then you know, like, oh, maybe the data doesn't fit. Let me try support vector machines. And you guys in this class will learn this level of detail for support vector machines, trees, gradient boosted trees, XGBoost. You will learn this level of detail for every single algorithm that's out there. And then how do you learn which one works best? Trial and error, and then obviously having a look around at kind of stuff. And there's also like rules, like for instance, there's Bayes' theorem or Naive Bayes, it's known for how good it is in spam. So over time, you get a feel for which algorithm to apply, but there are different algorithms. It's not always the same one. Did that answer your question? Or did I make it worse?
No, you answered the question. Thank you very much, ma'am.
Okay, Kat.
Can we go back to the lovely drawing you made?
I am going to unpack the tablet with the stylus for the next class. I swear you won't have this level of beauty.
I just want to clarify. You see, every time you're jumping on that point on that curve, that is the gradient descent, right?
Yes.
So if the model is guessing on each point, how is there a way that you can track the guesses to ensure that you're landing as close to the bottom as possible? Because if it's a U curve, you can easily overshoot it.
Yeah, it's called your learning rate, and all of this is coming. Okay, so
so is there a formula for it?
Yeah, and actually the formula you guys are going to learn in logistic regression, the log likelihood formula, which we're going to do in the next class. The most popular for binary, like this is the most popular function that's used for this is binary cross entropy. But what you will do is you will have a cost function, and it will make a lot more sense after the next class, or a penalty or a thing to be like, okay. So a good example to use is something like this. Let me refresh this. So this is blood glucose, okay? So we're going to use, I am a profound diabetic, so I could actually do this for you. So one ABC. So let's say the patient has the alphabet test, the HB1AC score of 30. That's bad, okay? He is definitely diabetic, okay? And then this one has 5. No diabetes here, okay? Then we go and we apply the formula and we come out with an answer. Okay, so we go do all the things. We go and we say, okay, I have got a slope and an intercept. I have put it through sigmoid and I've come up with an answer. And it comes out this dude is not diabetic. You'll be like, well, this dude is very diabetic. It's not diabetic. This is like go to the hospital, get on the insulin, popo has hit the fan. So then we go like, okay, to calculate this, we had a slope. That's not a slope. We had a slope of 5 and we had an intercept of 1. Okay. And we came out with not diabetic. Okay. We were 90% wrong. We were far wrong. Okay. So what we're going to do now is we're going to go and we're going to work it all the way back. And the gradient descent is like nested dolls, but I don't want to kill you guys yet. Okay, so we are 90% wrong. So we now need to get less wrong. So then we're going to say, okay, because I'm very wrong, I'm going to make a big change to my slope. I'm going to make that slope 50 and that intercept 10. I'm going to make that big change. Then I'm going to come again and I'm going to say, so let's say we came out here that, let's just write numbers. We came out here at 4. Okay. Very wrong. Then we go like we are far wrong. So what if we just say this is our Y? We know that the guy's 1ABC was 30 and our Y hat came out 4. So we're going to say 30 minus 4 equals 26. Stuffing wrong. Okay. Big change to the slope and intercept. Then we come out, okay, our Y hat is actually now 15. Okay, so if we minus them from each other, we are now getting to 15. It's much better. I must still make some changes to the slope, but not that bad, you know. So now we're going to say, okay, let's make this guy, instead of by 10, let's say this is 55. And this is 15. We do all our calculations. We come back and we say, oh, now it's 10. Okay, it's better. We keep making those changes and we keep adjusting these. What will happen is convergence will happen. And we'll start making changes like, oh, now it is 60.001 and 16.001. Okay, so if I change that now to 002 and 002, whoops, I have overshot. I have to bring it back. But those changes are so minute that the model will start swinging. Oh, I've overshoot, now I'm over here. Oh, I've overshoot, now I'm over here. So actually in this range, it's my best optimal. I have converged over here. Because if I make little tweaks this way, I overshoot. If I make little tweaks this way, I get back this way. And the tweaks I'm making are so small that I actually stay in this acceptable range over here, that this is actually the best possible slope and intercept. Did that make sense?
Uh, yes, I'm sorry to hijack again, but then what happens if your absolute value, that 30, isn't known? Like, let's say at the time you don't know that 30 is the
You
diabetic answer or not.
always know, because this is supervised learning. You always have an answer to check against.
So in the portion of the credit, let's say somebody is earning 30K or whatnot, and they're asking for a loan of 30,000, just like that other guy. It's roughly the same as his salary, but his credit was like 555 or something.
Yeah.
And that was wrong there.
So
where's the always know for an individual account like that?
So you're talking about the main knowledge, but what we have in this data set, the bank has told us, for this dude, I did not approve the loan. There's your answer. For this dude, I approved the loan. So you always have why to work back on. In supervised learning, you always have the answer.
Okay, I got it. Thank you.
Okay, no problem. And then, and you know, but the best thing to do with this kind of stuff is go and look at data that's known to you, like something at work you work with every day. Make yourself 10 records and work it out, and you'll see how you go wrong. And in the next class, we'll start looking at, clearly the bank here ain't gonna love us. Oh, I'm wrong. The loan was approved for this guy. The loan wasn't. No, man, it was not. I was right. Clearly, the bank is going to not love us with our first iteration, because we're going to give everybody a loan. People with totally bad credit scores is going to get a loan. And if we look at some other data sets, like at Kaggle, if we look at, I want to see if it is for phishing. Phishing URL dataset is interesting to look at. So if we want to classify a phishing URL, am I going to get to that dataset easy now, or am I going to suffer? If we look at the phishing URL dataset, if we download that guy, oh, yeah, okay, Kaggle. And then you have to go click download again. If we look at that dude, listen, whatever you see in my downloads, like every campus has a psychologist, even the online one. Okay. Oh, I should have extracted that. So here they have labeled URLs as bad and good. And this is where domain knowledge, oh my word, how long are these URLs? This is where domain knowledge is super important. So let's look at bad URLs. These are all bad. These are all phishing URLs. Okay, so those are bad. Let's go find some good ones. Oh. Here an example of good URL. So you would have to have domain knowledge. So, and then I'm going to say how to check if a URL is a phishing URL, because I don't actually know. Okay, no. Estimate the domain, expand the shortened list. But there are ways to check if this URL is a phishing URL. Okay, so good means it doesn't contain malicious stuff. Bad means it contains malicious stuff. And then there will be examples. So if you go look at the, I wonder if let's go look for code example. There's a they've done a nice EDA in this code, but you will see that they will lift out, because they have domain knowledge, they will lift out the stuff that tells them if this is a phishing URL or not. So if you work in the banking sector, you know what a bad client looks like. So you will see if it is a client that is someone, you can eyeball that data. Like, I know what good sensor data looks like. So this isn't a nice example, but let's just say, what does a phishing URL look like?
No, I get it. I think you were very apt in your explanation. Thank you.
Yeah, so then that will just help you look out for the stuff. So there will be type squatting, character substitutions, deceptive domain, URL shortness, mismatch things. So that is because you have domain knowledge about that. You will see what that phishing URL looks like. So if you guys are in the fintech sector, you will know. And that domain knowledge is invaluable. And if you guys want to wonder how it works, so like if you are like, for instance, I work for EMERIS as a research scientist, and as much as I don't like to train stuff out of my fields because it like feels I really understand, sometimes I do get asked. Like I was asked to do a something that reads in all of our assignments and tries to predict if that assignment is going to touch SDGs or not, the Sustainable Development Goals, and then to say how many assignments are likely to answer SDGs, how many ones actually answer SDGs. I wasn't an expert on SDGs, so I went to sit with Dr. Rika, who works for us, who's like phenomenal in SDGs, to get that domain knowledge and work alongside her. So if you're a data scientist working outside of your domain knowledge realm, you will always work with a subject matter expert. And so I sat with her for 2 to 3 weeks to train that and show her deep EDA of what I pulled out, show her examples of what the model put on. She'd be like, yeah, that's exactly wrong, or no, you've missed the mark. So that's how it works if it's not a domain that you are comfortable in eyeballing or really deeply understanding that data. All right. Is there any other questions? Was this stupid difficult? Are you guys freaking out, or are you going to be okay?
Their hands up.
Andrew?
Sorry, Serena. I wanted to ask, with the whiteboard, with the calculations you were doing there,
My nasty ones.
yeah, was that essentially what the solver does to adjust?
Yes, 100%.
Okay.
That's what we're going to do with the solver. You got it.
I see. Okay.
That's exactly what the solver does. Now I want to ask you guys this. Think back to your first lecture about linear regression, where you written all of the 9 million things like, I can't do this, I can't do this, I can't do this, it's so hard. What is this? Now think back about linear regression. How hard is linear regression to you now?
It's the easy stuff compared to what you're explaining now. What the hell?
Yeah, so do you guys know what? Next week, logistic regression will be the easy stuff because it's just repetition.
So that's, you just added learning rate as well while we were checking here, while we were trying to adjust to others, then you add another curveball. I'm traumatized.
No, and one of the colleagues mentioned here, it just feels. I also said it feels like this is intersecting with actuarial science, because why is this needlessly complicated and simple at the same time?
That's how it goes. It is needlessly complicated and simple, but find the simple. But remember that we need repetition. So in the next class, we're going to do everything we've done in this class again and apply the cost function and the solver. So you can see it all come into a whole loop. And then if you're doing the one-year structure, you'll apply the machine learning algorithm and see it translate in Python. And also, you guys, the things need to percolate. You need to give it time to trickle into your brain. I think you guys are doing great. I mean, yeah, and it's okay to be afraid, and it's okay to feel like you don't know what's going on. Let's talk again after tomorrow night's class. Okay, when we're going to break it down nice and simple. And then I've made some infographics for you guys that I will upload. That's basically the steps of what you do and why you do them. And that's all you remember. You now take that log odds stuff out of your head. You know it now. If you see someone say log odds, you go like, oh, it's just mx plus b. Nothing serious. Why is it log odds? Because I want to be able, not tomorrow, sorry, next week. Oh, and then next week is your last class with me until you do neural networks. Or maybe support vector machines. We'll see. Maybe someone else will pick us. I don't like love them, but somebody else might pick them up. But we'll do this again. And you'll promise you will feel about logistic regression exactly how you feel about linear regression now. Okay, Kat, you will always have access to me. You'll always have access to my recordings, and you'll have access to all the lecturers in the course. And you can always ask them questions, and you'll always have Nadia. Okay. All right, guys, I think you must be pooped because it is now 9:15. But good job, and it's fine to feel freaky outy, and it's fine to be nervous. We'll do it again in the next class. Yeah, please go rewatch the recording and ask me questions. Please WhatsApp me questions or find me on Teams. I really don't mind answering. This week I haven't been, like last week and this week, I haven't been the best in answering, but I'll be better this week. That's just 2 busy research weeks for me. Okay. Now, go hug your emotional support animal. Have a good night's sleep. And I promise you, you can do this. Okay.
Oh, Serena,
Yeah.
if you stop the recording, I want to quickly show you an Excel. It will take
Oh,
you
my word,
30 seconds.
But shouldn't we do? No, let's record this so other people can see it.
Oh, okay, cool.
What must we
Because
do?
I work with data at work, so I live on Excel.
Okay, I don't. So let's go show me.
So, like for example, if you go to A2, and let's say you want to quickly highlight from A2 all the way to AF, you can press Shift and Control, and then press your arrow to the right.
Oh, look at this.
Yeah.
So are you going to? Oh my goodness.
Yes.
Okay. Yes.
And then
So,
if you want to control specific ones, so let's say Control Shift, go to the right.
Yeah.
And then down while you're holding Control Shift. And let's say you don't want the last value, you let go of Control, but you keep your finger on Shift, and then you click the up button. Yes. Okay. Now you can do that for individual data sets, and you'll move quickly.
So listen, at the end of every class, gooi us your best Excel tips. Okay.
Awesome. If you guys work with like large data sets where you're working with 2 pieces of data at the same time, I can show you how to do like VLOOKUPs and all of that nonsense.
I can sort of do a VLOOKUP and an HLOOKUP, but actually that will be quite nice to do as well. And there was pivot tables also. If we're at the end of one lecture, you can show someone some pivot tables.
Oh, those are very easy. You'll laugh at how you couldn't figure it out.
Okay. Right. So deal. End of every lecture, we have 10 minutes Excel masterclass.
Hello. Can you pay me, please?
Yeah, probably. Let me ask Afeni. Let me play with Afeni's budget. Okay. All right. Okay, guys, thank you, Kat. That was really useful. And guys, listen, nobody is ever too old to learn. If you see something, you go like, oh, that's actually, I can do it. Like, please share. I mean, we can all only learn from each other. I mean, this is going to make my life significantly easier. I won't drag the wrong columns anymore. So go have a lovely evening. This video, Nadia will upload this recording. And find me. I want to buy a Ford Ranger. Me too. So, but find me if you need help, and please ask me questions. Don't be afraid. Okay, and if you see me online on Teams, please ask. All right. So, and remember, this was round 1 of logistic regression. Round 2 is coming. It will settle. Now, go and have a lovely evening. Okay. I'm going to stop recording. Good night, guys.
Good night.
Good night.